Welcome. Something about an observation I recently made when experimenting with manifolds. Unlike in the usual framework of Mayer-Vietoris, where you glue things together, I'm looking at manifolds which are half open, half closed. So here I call the closed part the boundary, the closed part of the boundary I call the beginning, and the open part of the boundary I call the end. Now we can glue things together if these match, if the ends and beginning match, and you can glue things together and you get a new manifold. So this can also be empty, and like here we have examples, and the definitions are all here. This is a self-contained, again, summary about all the definition. Everything is finite. We take finite abstract simplicial complexity. We define what manifolds are, what spheres are, what the boundary is, and open. We have a topology, so we can talk about open sets and closed sets. Also what the cohomology is. This is very down to earth. So the cohomology we take just as the kernels of some matrices which we define. So this is really something 21B student, we teach linear algebra this semester, and so this is something you can understand very, very early on. This is all discrete finite mathematics, linear algebra. A lot of more experiments have to be made. I think it's actually pretty easy to prove by just the heat flow. You have the cohomology here, and if you fuse things together, the cohomology can flow from one part to the other and still remains a cohomology class, a harmonic form. So we think about harmonic forms which kind of fuse together. So this is really disjoint, right? There is no intersection here. So this is a closed boundary, this is an open boundary. So from the Euler characteristic, it's immediately that the Euler characteristic adds, right? Because they are disjoint sets. So this is just counting, super counting. And there is also a relation between the cohomology and the count. So there is quite a nice theory behind this, but it's all very down to earth because we just deal with matrices. Just explain this, I keep this short, explain this with kind of the simplest example which you can really look at is the half-open interval. So the half-open interval is something which is, the cohomology is trivial. The Betti numbers, which are the kernels of these matrices, they are 0 because these matrices are invertible. So there is no cohomology living here on that. If you look at the closed interval, of course, there is a cohomology. There's the zeroth cohomology, so that the Betti vector would be 1, 0. But here the Betti vector is 0, 0. And now you can glue them together. You can glue one of these open interval, a half-open interval, you can glue together with another half-open interval. You get again a half-open interval, and here the Betti numbers, of course, they are again 0. This is again a half-open interval, just with a barycentric refined version, kind of topologically equivalent. This is all topology. It's very important that we have a topology. And by the way, this also works for higher characteristic, higher cohomology, and I'm also experimenting with Wu and higher characteristic there. And so it seems to work all the time. What needs to be in place is orientability. I mean, one example which doesn't work is a projective plane, and you take an you take a projective plane and you take an open disk away, and the open disk has a cohomology which is just a 0, 0, 1, expected 0, 0, 1, but this cohomology cannot kind of live on the projective plane. So that's why the fusion rule doesn't work there. But it's not bound to 2 dimensions. This is kind of a pictures of 2 dimensions, right? We have genus surfaces of genus which you glue together, and but this can be higher dimensional manifolds. This is rather arbitrary. It's also not bound only to manifolds. It also works for quite general things like this. If you take more general objects, but this has to be investigated. So first of all, also this identity doesn't hold for multigraphs, for sets of sets in general. but it needs some assumption, like in an open set in a simplicity complex, or a simplicity complex, a closed set in a simplicity complex. So here, this is a nice example. We have we have here no beginning, we have only an end, and here we have a beginning. So this is kind of a very small world. If you glue them together, you get the two sphere. And here you kind of you can just write down these matrices. Maybe I will display the matrices. So they are, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9 matrix. And here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 times 17 matrix. And so in both cases, you can compute the kernels of the Laplacian, and you get here, you got 0, 0, 1. So there is a cohomology which lives on that open half disk here. Cannot escape, right? Because, so there is actually kind of this 2 form lives here, but it cannot kind of diffuse away. So here there is only a 0 form. So here comes a 0 form, here comes a 2 form. So there's kind of something like Poincare duality also coming in, especially kind of, let's look at this case. In this case, so what we have is this torus with an open hole. You cut a hole here, you cut a closed hole. So this is an open, has an open boundary. Then the cohomology is 1, 2, 0. So there are two harmonic one forms. I did the computation for how we get the cohomology of this. I got with the fusion rule for that. If you glue them together, here we get this, which has the Betti vector 1, 4, 1. So this is a genus 2 surface here, which has been obtained by gluing together two genus 1 surfaces. So this is just a beginning, and I hope to say more about this in the future. That's it for today.